Hello everyone, it's April 3rd. Alright, let's do this. Lowest common ancestor of deepest leaf. Oh, lowest common ancestor is not an easy problem. But this is lowest common ancestor of deepest leaf, so it's slightly different. So give the root, return the lowest common ancestor of its deepest leaves. The node of is a leaf if only it has no children. The depth of the root is 0. If depth of node is d, the depth of each of the children is d plus 1. Yeah, the lowest common ancestor of a set of nodes is the node A with the largest depth such that every node in S is in the subtree with root. The lowest common ancestor of a set of nodes is the node with the largest depth that every node in S is in the subtree of root A. Lowest common ancestor of its deepest leaves. Lowest ancestor of a set of S is the node A with the largest depth such that every node in S is in the subtree with root A. Okay, so in this case, what are we returning? Oh, we're returning the root. We're returning the tree node. So we need to find the deepest root. Okay, I have a question. 208. No, 74. What if I add another one? Expected is 3, right? Expected is the full thing because I add another node here, so these are the deepest. So we basically need to find the deep. Well, what if the deepest is only 1? Well, we can try. This is actually good. Well, we can try. Let's say 74. And we have to go lots of no. No. 9. So I expect is 7. Can I hear 3? Oh. So we don't have a tree view anymore. So I forgot how. Because I go here, I 7, 4, I say no. Because 9 could be here. Or 9 could be here. Depends on how. Alright, let's try this one. We have 0, 1, 3. 0, 1, 3. no 2. Oh, the least lowest common ancestor of one node is itself. Oh, I see. Okay, so we can do a traversal, like just a regular traversal. No, I don't speak Portuguese. We can do a regular traversal and, you know, find who the deepest leaves are, right? We can do that. So I'll have bunch, okay, deepest leaves. And then we need to find their common ancestor. Common ancestor. Oh man. There is an algorithm to find common ancestor. I don't remember. I really do not remember how that one was done. I might even have it somewhere here. It's for the common ancestor. Yeah, I don't remember. So we can either do that, or because the constraint is quite loose, right? It's only 1,000 with everybody is unique. So it is possible that we produce the actual path to every single root leaf, right? So we just go down for every path, we save it somewhere, right? Every path we save it somewhere, and then what? We save it somewhere, and then what we need is what we need is, once it's done, then we'll find the one with the largest, right? We'll find the one with the largest. No, we can't always prepare the one with the largest as we are traversing. So by the time we finish traversal, we'll have a list of paths that has the deepest, longest path, right? And then once we get there, we simply go just from the leaf towards up and find the first one that's the same. Yeah, that one definitely will work, but I am curious because I forgot lowest common ancestor. There is a problem that can be solved by this. Oh, what the hell is this? ANC matrix. What's ANC matrix? Kth ancestor. What the hell is this? Lowest common ancestor. Depth and this. So we create ANC matrix. Yeah, you see we have the p value, q value, and we compare the depth. I think this is just to swap, make sure that the depth of p is smaller than q. So q has more depth. And we run a kth ancestor. The difference between p and q, to make sure p and q, now they're on the even, right? They're on even depth. So if they're the same, then we return that. Otherwise, we get the level of one of them, which is just the same, right? And then we find their level ancestor, right? So they go back up. So if these two are not equal, that means we haven't found it yet. So we do it again. We find a new level. Yeah, basically just the current level of these two. And -1 because the current level doesn't work, so we go one level above. Right, one level above. Otherwise, if they're equal, then we right, if they're equal, we remove one level. Yes, we remove one level. When they're equal, it means we don't know, right? They just shoots up too much. So we reduce one level and then we try it again. Right, reduce one level and try it again. And eventually we'll get level down to 0. And that's when we have it. So this is ancestor matrix, I think. That's what it is, the ancestor matrix. And we have this also, case ancestor. We use ancestor matrix. So what is ancestor matrix? Ancestor matrix. If node is none, okay. Depth node.val. Oh, ancestor matrix, we produce two things. We produce depth and we produce ancestor matrix. So we get the depth first, and then ancestor node of value append parent. So parent is my ancestor, so I put parent there. And then what? And then we say while one left shift I. What the hell is I? It's smaller or equal to depth. Is that like binary lifting, I think? Oh yeah, this part is really hard to understand, I remember. So we just find more ancestor. It's going to be the current node's ancestor, its ancestors, I minus 1th ancestor. Because you can find your ancestor, right? And yeah, it's a binary tree, right? It's a binary tree. So your ancestor, so you want to find, so yeah, that's why the just I minus 1, the half not a full level, it's half the level, right? Half the level. You go half the level up, so you go to your ancestor, and it's go up half the level up. That one half the level up will be the one for you. Yeah, it's like if you want to find the 8th level, what you do is you find the 4th level ancestor, right? You want a 4th level ancestor and that ancestor's 4th level. So now to find the 4th level ancestor, so it's you go to your ancestor's 4th level. Right, you go to your ancestor, find its 4th level. Go to immediate ancestor, because that's the 0 level, right? Go to your ancestor, find its 4th level, and from that one's 4th level, then that's the 8th level for you. Okay. And we work from top down. All right. Yeah, this is pretty tough. the binary lifting is pretty tough. I don't think. I'm not sure what other method have I used to solve this. I don't remember, honestly. Oh, find left, find right, find self. Yeah, I kind of remember that. But the binary lifting is the most fun, but also difficult to do. Look at the normal distribution here. So nice. Oh. Yeah, this is just say, is the left contained, is the right contained, is self contained, right? If found left, found right, found self, and we haven't found it yet, then we set. I wonder why it's not 2. Yeah, if it's found self, found right, we'll set. We found left, found the right. So it's in the left, it's in the right. Then yes. If all 3, then yes. We set a current node, right? If we want to say the current node is the ancestor, then we need to find the right and find the left. So yeah, that one, right? Or we find the left, we don't find the right because it doesn't have a right, and it's just on the right. Right, the node is the self, right? The self doesn't have a left. Oh yeah, okay. I kind of just went through this one more time, but yeah, it's tough. It's tough to get. But this one, I think we're just gonna use the method I just talked about, which is very straightforward, and we'll get it done for sure. Okay, let's try this. What do we need? Well, I believe we need a DFS. We can call it void. Right, and we need a okay. We need a vector of longest path. Ooh, that's not right. All right. So we're at node. Every time we do node, oh, we have also in the path. this is the path, right? Okay, so when visiting the current node, we always put it in, and then we will check if it is. Yeah, we'll handle it first. Right? We say path dot push back. We always put node in. Okay, and then we say if node dot. No, I think it's this, right? Left. If not, dot left, and not node right. Okay, so we had leaf now. Now in the check, if longest path dot empty, if it's empty, or longest path 0 dot size is equal to current path dot size. Either works, then we will push it in. We just say longest path dot push back pass. Ooh, we need to copy it. We can't just push it in. How do I make a copy? Actually, I don't know. Copy vector. Well, we can always do that. Maybe I do that. Yeah, I don't know. I feel I'm more comfortable creating a new one. Copy. Oh, I push it in. Then what? That's it, right? We push it in. Now we say else. If it's not empty and it's bigger, we can have else if longest path 0 dot size is smaller than path dot size. Right. In that sense, maybe we should do it outside. What do you think? As a copy, right? So we'll do the copy. Or if it's that we need to reset. How do I reset? It's a longest path dot resize. I think it's resize, right? clear vector. Okay, I think I'm gonna call clear. All right, so what else? If the size is smaller, then we just basically don't deal with it. Right, and then this is if it's a leaf. And we also has this else if node left, right? If node left, then we just do DFS node left longest path and path, like else, which is node right, the df node right longest path and then path. Once all of these are handled, okay, then we say path.pop back. So it's like backtracking. So for here, what we do is we will longest path. DFS root I think we're supposed to pass this by reference. Okay, so root longest path. So when this is done, we shall have the longest path for all of them. Now we should go from right to left. N shall equal to longest path 0 $size. At least we'll have one. And then we'll go from right to left. For I equals a minus 1, I large equal to 0, I plus minus minus. Okay. And we have to go from all of them, right? So we say for j is 0, j is smaller than longest path dot size, j plus plus, right? So we do just like pairwise. Okay, let's do this way. J equals to 0. Right, then we'll compare j and j plus 1. If it's equal, we'll compare j plus 1 and j plus 2, right? Eventually compare this. Right, if it's good, we move on. So we'll come up with that, and then we'll come out. So we'll just say while j is smaller than longest path dot size. Because I can take minus 1, minus 2. So if it's smaller than minus 1, and I'm gonna start this. and longest path j I value is not equal to, right, longest path j plus 1 I value. So if they're not the same, yeah, if they're not the same, that means it's not here. So we'll do j plus plus, right? No, it's if they're the same, then we do. If they're the same, we go, right? If they're not the same, we jump out. And this should be smaller than -2. But I can do -2, so it's -1, yeah. So blah blah blah, once we get out, then we can check j's value. I should say if j equal to longest path dot size -1. Right, so j moves to n, which means we have found it. We have found it. Right, this is where we found it. Then we simply just return longest path j I. Right, we just return this is the one. Actually, cannot use j. Oh yeah, I can use j. I can use j. Right, so the j's one, the i's, we found it. If it doesn't, right, if it's not, it's too small, then what we're gonna do is we abandon it and then find the next I. Right, I will move forward, and then we check, move forward, and we check, move forward, we check. Now, I think there is a better way. We can pop, but I mean it's the same. So would it be that we don't find any? I don't really think. I don't really think it will happen. So we can just say a tree node here, right? And then notify that we shall never reach here, right? We shall never reach here. Okay, let's try this. Oopsie doozy. Oh my god, that was pretty bad. I got 6. That ain't right. How'd you get 6? I don't know why it will happen. Actually, this way. If not a not, right, then we do that. If longest is empty, well, I mean, as we first start, yeah, as long as it's empty. So we push it in, right? And yeah, then we return. We pop it and we return. Now we shall come here. We shall come here. The longest path I clear it. I am not sure why it's not working. No, no, let's just print debug it. I want to know what we are at, and then let's do 0 font size. All right, kind of poking under the hood. Oh. Wait, no. It's just me making a mistake. I thought I made the mistake of getting the name wrong. No, it's just. Alright, this should be paths. Alright, so we have 6 and 1. Oh, I remember why. We have to go both. Ah. I don't know why I don't do that. So like I never really go to the right. Yeah, that's stupid. If not node, then we just return. As simple as that. Otherwise we do whatever we need to do. We have to traverse both sides. I don't know why. Yeah, there we go. It's a weird mistake. But it's alright. We got it done. Where's my print statement? I remove all the print statement. Let's write something here. First, find the path. Find the paths for all the deepest leaves. Then compare across all the paths, all the longest paths to find the first node shared among them all. I feel it's O(n) squared. What's n? Well, this is, yeah, I'll put O(n) squared. I'm not sure if it's exactly O(n) squared, but it gotta be close. This does not feel fast. But since we only have 1000, I think O(n) squared will probably just squeeze us in, maybe a 5%. Oh, it's actually much faster than I had expected because it's so small. Because the number of paths is yeah, it's oh wow. Recursion. Okay, so let's see. I didn't read it. Hopefully I have some good understanding of recursion to do this. How do you do it just with recursion? Well, I have depth, right? And basically when you come back, I need to know that I am. How do I know that? The paths, not the path, the depths that the deepest that I can see. Ooh, that's it. The deepest I can see. For each root, I'll say the deepest I can see. The other one say the deepest I can see. On the left, on the right. Yeah, basically just the deepest I can see for each one. And as you go, we will update the deepest. So when you rewind, so the first one that can see the deepest, right? The first one that can see the deepest is your solution. Oh, let's see. Yeah. Okay, let's try recursion. Let's reset this one. So we can solve this by recursion directly. Let's try solving this with recursion. So with recursion, I probably need to return a tree node here. DFS. How do I know the deepest though? We can keep a record of them. For each one, I know my current level, right? And we'll return the deepest, right? The deepest that I can reach. The deepest I can reach. So basically, for each node, I'll go my left, I'll go my right. Will tell me the deepest that they can reach. Right, the deepest they can reach. But I don't know if I am the one. I need like a temporary thing. Can I have a temporary thing? Ugh. Right, so we are at the node, and again, if not node, just return. Okay, so if we have a node, and we have the current level, and actually we should return int. Yeah, I think we can just avoid that. The depth. Yeah, I don't think this will happen, right? So basically, at the node level, if not node left right, so this is leaf, then we just return. Then we have the current level, right? I don't know. No pointer is 0. If one side is larger than the other side, so we start from DFS root. What does this give you? The depth. The depth, that's what it give you. Okay. So I have one side is longer than the other. What am I returning? If the left is longer than the right, then I'll return the common ancestor, the lowest common ancestor. So lowest common ancestor is this, and my current depth. Okay, I understand if left is deeper than the right, then we use left. If left is not as deep as right, then we use right. I understand that. Okay, so my question is, if the left is equal to, then we will return. Ooh, because the first one that got returned is taking the advantage. Oh Lord, this is good. Because the first one that got returned is the true self, right? Like the first lower common ancestor. And you encounter it and you return that one, and that's the true value. Any subsequent roots, they don't return themselves because they might still return themselves though. Because you do left, right? You do left. Hold on, let me think again. Jesus. You do left and you do right. So if you do left, if this gives you the same as the right, okay, but if I do left here and the left there, they will give you the same as well, right? How? No, DFS returns. Okay, DFS returns the lowest common ancestor in the subtree. The lowest common ancestor in the subtree. So if I go, I'm at this level, right, and then we have, so I have to say the lowest common ancestor in this subtree. Okay, whatever it is. No, so whatever that is, then if the length is the same, then I am a new ancestor, right? If the length is the same, then I am the new ancestor. That is correct. I am the lowest common ancestor if the length is the same. Well, I am not a low ancestor if the lengths are not the same. Right? If it's not the same, then on the longer side you have the lowest common ancestor. Makes sense now. I think I should do this one more time. I mean, we solved it, but it was not really satisfactory. Yeah. And I think the solution is quite good. Alright, anyway, that will be it. I'll try to solve it one more time tomorrow. Have to get familiar with this recursion kind of way of thinking.